All right. So today we'll talk in more detail about page tables, virtual memory, and such. This will lead eventually to our next project, which has to do with mmap. Who's used mmap in previous class or project? A couple of you? Okay. So, well, that's not too important. We're just going to be implementing it. The programs themselves are already provided. So, first, did we have any questions on the homework? Homework 3? Yeah.
How many programs can be writing to a device?
How many programs can be writing to a device? Oh, that's a very good question. I think generally we probably should have a lock on the device so that there's only one at a time. For this homework, there's only going to be one. So don't worry about multi-threading. Any other questions? Nope. All right.
Actually,
yeah.
Could you show the solution of homework 2 again? You cut it out of the video lecture.
No.
Okay.
I mean, so if you're here in lecture, then I will discuss the homework, but unfortunately the homework solutions are not going to be online. Can't very well repeat it over and over. Thanks. For you. You didn't miss that much for the homework too. Basically, it's a very small program, right? For homework 3, it's not based on what's going on in homework 2 at all. It's kernel stuff. Right. Okay. So I figured out what's going on with the clicker. So I'll try it today again. There's a cool little bug where if I have this control, see this little control here? If I have this one on my screen when I hit play, it crashes. But if I have it on the big screen, it's okay. And I was actually talking to iClicker support about it, and they said, yeah, it's a known bug. Can't do anything about it. You'd think they could release an update, but... anyway, so let's try a couple of these things. Let's try this one first. So the channel is AA again. There it is. And now I can safely move it over. So I'll do that for a moment. So parameters in C functions go on the stack, in registers, both. Depends. Okay, so I'll pull this over. We have 9 responses. That'll have to do. All right. There's no need to adjust after you see what other people are saying, since you're not getting a grade on this. So this is sort of just to get a discussion going. All right. So some people think it's on a stack. Anyone care to defend that? Yeah.
Well, like if you have a lot of parameters and you have like a finite number of registers, like you can't put a lot on it. So like putting it on the stack, you can just like the ones you're using, you can just put those into the registers, and then if you don't need it, you know.
Okay. So you're saying like it's really not practical to use registers because it's a fixed number and you can have any number of parameters to a function.
Yeah.
So it's got to be the stack. Well, nice deductive reasoning. But there is an alternative to that. And I guess that's the answer that the rest are going with here, both the stack and registers. And that's actually the case for a 64-bit. So here, there's quite a few registers. There's 15, 16 of them, 14 of which we can use for passing in parameters potentially. I think we only use the first 6 or 8 or something like that. So the first 6 or 8 go in registers, and then the rest will have to go on the stack because there isn't enough room. Also, if you're passing in something by value, if you're passing in a struct by value, say it's not a struct node pointer, it's a struct node that has a size that's larger than 8 bytes. Well, it can't go in a register. So those always go in the stack. But the correct answer is actually this one here. Depends entirely. So on AMD 64, the calling convention used for Linux and for x86, because we're using GCC, that's the standard. It is both the stack and registers. On the x86 32-bit, it's just the stack. And there's Microsoft convention, there's all sorts of other conventions. It all depends. So whatever the compiler feels is right, whatever's been specified for this platform, this operating system, this is how we call functions. That's how it works. But yeah, generally, it's a good idea to use the registers if you can, because it goes a little faster. And that's pretty much it. Okay, so let's switch to another question. Oh, let's see. I have to move this over. Aha, I moved that one. This should work. Okay, so we'll go with this, parameters to BIOS interrupts. Four, 5, 7. Look at that. And we have consensus. See, this is what happens when we do homeworks, right? So that's sort of the point of why we have so freaking many homeworks in this class. There's so many different concepts, and they're not all that complicated, but there's just no way to keep track of it all if you're just reading a textbook. So we've got to grind it in a little bit. And besides, if you're supposed to be an expert in anything, programming is good to be an expert in if you're a computer scientist. The idea is you need to spend 10,000 hours doing it. And once you spend 10,000 hours, you probably are an expert. We're not going to get to 10,000 hours in this class, and probably not through your entire degree, but let's get a good start on it, right? That's also another good point here. Okay, so let's do something a little bit harder. What do we have here? Oh, that one we already did.
You want to stop the other question?
Oh, that's fair enough. Okay, so yeah, let's do this one. When switching to 32 and 64-bit mode, let's see, what happens to the BIOS functions? We didn't talk about this, so this one you're going to have to reason about. So when we switch graphics modes, right, the picture clears. So not entirely obvious what should be happening to BIOS stuff when you switch modes, perhaps. All right. I've got, anyone still waiting? Still working on it? All right. So, very good. Yeah, the correct answer is C. So they do remain in memory. There's just no practical way, actually, of figuring out what to clear out. Yeah?
Speaking of the graphics modes in homework 2, you actually mentioned that the cache is not necessarily clear when you switch modes.
The cache. Sorry. The video memory?
The registers, yes, the video memory.
So I think what...
Does this have anything to do with this?
No, it's actually kind of unrelated. But we're talking about mode switches and memory changing. So yeah, in that sense, it's related. When you're switching graphics modes, it is clearing the video buffer that it's switching to. So you will end up with a blank screen when you go to graphics mode, or no characters when you go to text mode. This is just sort of what the BIOS was designed to do. There's no particularly good reason, maybe, other than there could be garbage in there, and it's nicer that it's back, I guess. All right. So the correct answer, yes, you too. The correct answer is it remains in memory. So the reason is that there's no real way to figure out, like, what should we be clearing, I think. Yeah. Okay, so BIOS knows where its instructions were before, but we could already have been writing over that. It's just sitting in RAM. If we don't want the BIOS instructions, we can overwrite whatever we want in there. There's nothing special about them. So now when we switch switch modes, we have a bunch of 16-bit mode instructions in there, and they're not of any use anymore. We can't call those, they're not functions. If we do an int, well, probably we already overwrote the interrupt vector. We don't even know where those functions start. It's just garbage in memory. But it's sitting there. You can just override it when you feel like it. Okay. Let me do one that's related to... I need to look it up in my booklet. And then we'll see. Where are you? Well, that's no good. I was looking for main, but I can't actually find it in here. That's kind of useless. Okay, let's do it this way. What is the last digit of the line that begins the memcomp function? And it goes A1, 2, 3, 4, 5. So now you get a little bit of, okay, let me restart this one. A little bit of practice with your booklet. Usually the questions will be a little cleverer than that. So I see some people flipping through lots of pages. That's not necessary. There's an index toward the beginning that has all of the symbols, and that specifies the line number. And we've got a fair number of correct answers. 5 is the correct answer. My only point there is there is a little bit of indexing going on in this booklet, even though it's paper. We can't necessarily search it, but you can look it up, and you'll find that useful probably sometimes when we talk about the fork function. It'll be a little easier to find using this, and there will be things like that in the exam as well. Okay, so. Let us move on to, let's see, did I have one more? Okay. Now we're actually going to talk about virtual memory. So why don't we do a couple of actual proper questions here. Let's start a new one. And most operating systems would use one page table per process, or one per CPU, one per socket, one per thread, or one per gigabyte. We've got 9 answers. I'll move it over. Okay, so very good. The page table defines the virtual memory layout of a process. Right? Threads are part of a process. You can have multiple threads in one process, but they would share the same page table. So if they're running at the same time, you would have 2 CPUs using the same page table. Or 2 cores using the same page table. And that's generally sort of fine, as long as you're just reading from it. But whenever you're making a change to a shared data structure, you risk having race conditions. The same thing happens with a page table. That's a shared data structure. And so if now both processors want to, for example, allocate more memory, then you would have to first acquire a lock, make sure that you don't allocate at the same time, overwrite each other's entries in the page table. And then finally, when you've made the change to the page table, you actually need to let the other one know, because there's a cache as well. Right? You have this, it's called a TLB, right? The page table cache. each core has its own cache, and so now once you update your entry, your core realizes this. I think. In fact, you probably have to run a little instruction on your core too to clear that out. But on the for all the other cores using the same page table, they have no idea. It's not like they get notified whenever a write happens to some random memory location. So now you actually have to send them a special signal. It's called a TLB shoot down. Maybe we'll look at that way down the line. But basically, you also have to let them know that, okay, those entries are stale now. Time to update. Okay, one last one of these questions, and then we'll move on. So, all right. Come on. Can't even find my pointer. There. Okay. It's the other way around. Okay, so the processor knows which page table to use based on, there is a page table entry in the struct proc. The instruction says something about virtual memory. I mean, so you only care about it when you have an address, right? You only care about page table then. Segment registers get involved. There may be a control register. Wow, this is good. All right. Look at that. It's pretty even. It's been fluctuating a little bit. I think we had a B was scoring better for a while there. Okay, so this one we clearly are not quite sure about. So let's talk about A first, because that's the most popular one. Struct proc is a data structure, right? How does the CPU know which struct proc to look in? It can't be that one. Probably. Unless we have like some other way of telling the processor, like, this is the proc we're dealing with right now. But this struct proc is actually very x86 specific. So the processor wouldn't know about our particular implementation of a process. In fact, the processor doesn't even know about processes. It's not something that it knows about. It knows about page tables and whether you're in user mode or supervisor mode and which instructions are privileged. That's it. All right, so whoever said A will have to change their mind. B, okay, yeah, very good. So we don't specify any page table in the address. The address is it's always a virtual memory address. Whenever you're in page or in protected mode with paging enabled, you're always just specifying a virtual address, which is an offset from, offset into your page table, essentially. Okay, so now we have segment registers. It's the next most popular one. Segment registers, they do exist in protected mode. They have some sort of similar function to what they used to be in 16-bit mode. It's the same story. You say like, oh, my segment starts at address 1 megabyte. So now if I do a jump to 5, if my code segment is 1 megabyte and I jump to 5, well, I jump to actually 1 megabyte plus 5. So it works exactly the same way. You really have this sort of this, what do we call it? Addressing. It's not a pipeline. Well, so we start out with, so we have a virtual address. Let's see, how do we write this? A virtual logical address. That goes via segmentation to just a logical address. So the segment says, okay, actually we should be, to just a virtual address. So they call it a logical address. These segmented things are logical addresses. Like I'm the 5th byte in the code segment, the 10th byte in the data segment. That's a logical address. But in protected mode, we have this virtual logical address. We start out applying the segments to get those offset in. Now we have a virtual address, and through the page table, we end up with a, actually they call this, maybe they call this a linear address. actually. Yeah. Through the page table, we get to a physical address, which is no longer linear. So here we have the virtual addresses generally go from, or the linear addresses go from 0 and up, right? But at every 4 kilobyte boundary, due to the page table, you could end up at a completely different physical address through this mapping. Okay, so anyway, the segments don't really help us find the page table. They do help us somewhat with the getting an address, but it's not for the page table. We set it up in, and I had this in our drawing. Pull this over. Or I think so. Nope. Anyway, so we have a CR3, control register 3, points at the beginning of the page directory. In 32-bit mode, there's this first level, the page directory, where each one specifies a 4 megabyte chunk. Inside that 4 megabyte chunk, the page table specifies 1,000 different 4 kilobyte chunks, which are the physical page frames. Okay, so the CR3, control register 3, points at the actual page table. So if you want to switch to a new process, you probably have some inside the OS things to take care of. Like you probably want to say, oh, this specify for the process, this is the running one, you know, some bookkeeping. But then there's something very special that you have to do for the CPU, and that's tell it, now I'm working with a new page table. That's how we create the process abstraction, really. We change the CR3 register to point at the new process's page table. Okay, so in 32-bit mode, just to repeat, we have a 32-bit address space. That's 4 gigabytes of potentially addressable RAM. Right? Those 4 gigabytes are divided into, we describe the entire 4 gigabyte address space using our page directory. There's 1,000 entries, 1,024 entries in a page directory. And then some of those will be filled. So here the process has filled 2 of them. That means we have up to 8 megabyte of process address space. And inside of here you can then see, okay, in fact there was only really one of them. It wouldn't look like this. Here there's only one of them that actually points at a physical page frame. The rest of them are empty. We'll see shortly what it means to be empty. But basically only one of these entries, it's not even the bottom one, some 4 kilobytes, somewhere in the middle of at the top of the first 4 megabytes. That's the only one that actually has some page mapped in, we say, which means you can read from those. But if you try to read from a byte over here, what do you think happens?
You'll get garbage.
You get garbage. There's one pretty good theory, but that's not what happens. It's not quite as useful as what we actually get. It's another thing that might happen. Segmentation fault. Yeah, it's very close. It's called a page fault at this point. Segmentation fault is an OS construct, but if you try to read from this one, there's actually a bit called present in there. The OS sees this one doesn't have the present bit set. That means there's nothing mapped in. Right? It's not like it's all zeros. That's not important. But one of those bits is a 0. That means there's no entry there to pay attention to. In that case, you get an interrupt or an exception. Exceptions, interrupts, they're pretty much the same thing. So whatever the program was doing, when it tried to access this bit of memory, it stops and suddenly jumps into an interrupt handler. Let's look at what the x86 interrupt handler looks like for this. You can go to trap.c if you like in the textbook, and I will join you shortly. Let's see. All right. Right, so I'm going to be using Emacs, I think, for most of these things, just because then I get these search functions and things. The unfortunate thing is then I don't have the line numbers, so it doesn't quite match up with what you're looking at, but the code will be the same modulus any bug fixes that I make to this code during the semester. What's that? Line number mode doesn't help because this is your line numbers are global across the entire x86 code. I mean, I could do it in the maybe we should try that. What's it called? x86.pdf. We could try this. Maybe we'll mix and match a little bit. Anyway, so let's head over to trap. Trap.c. Yeah, here it is. Okay, so this is where we end up. After a little bit of assembly, right, that saves away all the register numbers and so on, we end up in this, by now, somewhat familiar function, trap. In the past, the trap number was system call, but that's not it now. Right? Now we suddenly got a page fault. So we go down a little bit further. Here we're looking at the trap number. And it's not going to be an interrupt, an IDE, that's a disk. It's not going to be the keyboard or the communications port, the serial port. It's not the timer. In fact, it's none of those. It's not the spurious either. So we end up in the default. In this case, we end up in the default, and you'll see this, unexpected trap. Wait, if proc is 0. So this proc is a magic variable that points at the current struct proc. It's magic for now. We'll look at exactly how it works later. So if there isn't a process, well, then we have some real problem here. But otherwise, it's this one here. And this is, you probably have already run into this once or twice. So it says, oh, this process got this trap problem. Okay. So for now, x86 doesn't really handle page faults, right? Well, it handles it in one nice way. It kills the process, right? So we try to access the page. If the process is doing something ill-behaved, well, then we kill the process. And the system itself keeps working nicely. You know, this is one of the real benefits of protected mode. The process can't really do anything to bring down the OS. This is generally true unless you have a buggy OS. So you cannot blame the program for crashing your computer. It's the kernel that is broken. Of course, it can kind of tickle the kernel the wrong way, and then the kernel crashes. So I don't know. The causality is there, but it's not the blame is not there. Okay, but you know we could do much better here. So here's one thing that we can pull off with this setup. The process, if it tries to read from this address, about 4 megabytes up, we get some contents. Good. If we try to read from this page, we get a page fault. Okay. So the kernel now has a choice. It can kill the process or do something about it. Right. So what can we do about it? Send a signal to the process. Huh? We'll see signals a little bit later. Signals are way too complicated. Once you end up in a page fault, you have to take more immediate action. Signals are like a relatively heavyweight thing. But what you could do is you could send a kill signal to the process. That's kind of what it looks like in Linux. When the process dies, it looks like you got a kill signal, but in fact, you couldn't even stop it from happening. It's not a real signal, the kill one. We can do something else. Let's make the program work instead. So we're the kernel, right? So why don't we allocate a page frame, add a new pointer, and then return from the interrupt. In that case, in the case of page faults, the processor will try again. If you just return, it'll try running the same instruction one more time, and this time we have a page mapped in. Let's do that. We got another page mapped in, so now we can access it just fine. And what do we get back? Zeros, right? If the application tries to read from a new piece of memory it has never accessed before, it must get zeros. You know why?
RAM is volatile and temporary, so if there hasn't been anything written there for a while, it's going to be all zero.
Huh, interesting. So it's sort of a physical effect. We haven't been writing to it, and so whatever ones we put in there before, they went away. So this is actually not true. It's true in some sense. RAM is volatile. If you don't write to it, the contents do go away. But it would be extremely impractical for the machine to work that way. So the way it works is the RAM controller, like the little chip that sits next to the actual memory chips on this little piece of the stick of memory, it keeps rewriting those bits. So your bits don't go away. As long as power is on in the machine, if you wrote a one to somewhere in the memory, it'll stay there. Okay, so that's not it. It's not zeros because they went away, unless it's a rebooted machine. If it's if you lost power, then it's going to be mostly zeros in there. No, it has to be zeros, which means the kernel actually zeroed it out for safety. So what you could have otherwise is some careless user program. You typed in your password, you hit enter, it computed some hash or whatever, but the password was there in a string. And then the program is done, so it quits, and now you have the stuff sitting in memory. The memory got freed. When you free something, it doesn't necessarily clear it, it's just sitting there. And now the kernel goes and says, oh, that's a free page, let me hand that to this new process, and there's the password right there. That's not okay. We can't have accidental communication between programs. This one process can share contents with another process, but it has to say so explicitly, right? Either try to send something over a socket or over a pipe or maybe through shared memory. But you can't just have people spying on you. Did anyone attend the distinguished lecture today? Okay. We probably should try to get announcements to all undergrads. But there's a whole bunch of grad students here. You didn't go either. Okay. We have every year we have a series of distinguished lectures. There will be probably one every month. It's by some top researcher in the field who usually gives good talks, not just a good researcher. This time it was about a security problem. It's called the timing channel. Basically a way for one virtual machine in the cloud, you have two virtual machines running in the cloud on the same physical machine. He explained an attack whereby one virtual machine can read the contents of the memory of another virtual machine. And this is, of course, extremely bad. Now so they were able to steal passwords and log in, log into other people's accounts and take cryptographic credentials and all sorts of bad things. Anyway, that happens through a side channel, a timing channel, through very sophisticated attacks. But in this case, if the kernel did not clear out the memory, you could have one process with some passwords in it, the other process just stealing it, and one of those processes is going to be your browser. So now you're visiting some page, some JavaScript decides to allocate some more memory to see what passwords might be in the memory and then send it over to the web server. Right? This is completely unacceptable. So it's got to get cleared. Okay, so anyway, this is one way to handle it. Wherever you write, we just allocate more memory, and then we continue on our merry way. It's a pretty cool setup, because now it looks for each process as if it truly has 4 gigabytes. It doesn't have to bother with any memory allocation, right? We don't have to increase the size of the heap or anything. We just go for it. Just write wherever you want, and it will just work. Pretty nice. Except we don't do it that way, generally. Any ideas why? There's a couple of weaknesses here. I think this clicker thing is very limiting. I wish we could have a way to get, small answers. If I provide a few answers in a multiple choice, it is so lame. Right now, this is.
You can do ASCII in clickers.
You could do ASCII, yeah.
It's really tedious.
It's got to be a lot of fun. Yeah. Yeah. Okay. So anyway, I'll just take ideas. Yeah.
If a process doesn't need more memory, you should just allow it to you should have to write to the
Oh, okay. So, if a process doesn't actually need memory up here, we shouldn't allow it to just take it. But it could still, with a system call, it could just ask for it. And that's the same problem. Like, give me a gigabyte. I don't need a gigabyte, but give me a gigabyte. Right? So that's probably not quite it. I can think of a couple of reasons. So what if you have a buggy program? We often do. And they tend to crash on us now. In this situation, generally wouldn't. Or at least it wouldn't crash immediately. At some point, maybe it would do something else that was illegal, but at least it can access whatever memory it wants. And chances are we would allocate 4 gigabytes worth of memory sometimes, because this thing would just, if you have a buggy program, who knows what it does? But maybe it writes to every byte and increments. That's a possible bug. So now you allocate 4 gigabytes, and eventually you try to, eventually it wraps around, I suppose. Once you get to the top, and you add 1 to the address, then you're down here again, and it just continues. So I guess one reason here is we can catch an error earlier. If the programmer declares, I want to malloc some memory, or I want to raise the break to have some more heap space, then we know that was the intent. If they start writing outside of that, probably something went wrong, and we want programs to crash early. If we just let them continue running, doing random stuff, there's an increasing probability of that random stuff being something actually kind of bad. A program might inadvertently make a system call that deletes a file, let's say. If the program has the permissions to delete that file, the file goes away. But as soon as it's doing something it really shouldn't do, we should probably kill it. So that's one good reason, I think. Another one has to do with freeing memory. So if you just have all of this memory and you just write here and there, how do we return it to the system when we're done? Our program doesn't need all this memory anymore. We can quit the program, of course. That would be fine. But if the program just doesn't need so much memory anymore, how do we return it to the OS? We didn't allocate it in the first place. We just wrote to something. How does the OS know that we don't want it anymore? I guess we could write zeros to it. Clear it all out, and then leave it to the OS to see, is it all zeros? In that case, I will delete it, right? That seems a little impractical. Yeah, so I think that's probably another good reason. We want explicit allocation and explicit deallocation so that the programmer can say something about what they need. Otherwise, we end up pretty much just wasting resources. I don't have any other really great explanations at the moment. If you can think of some other ones, let me know and we'll discuss it. Okay, so here we are. Unfortunately, only 4 gigabytes worth of address space. Yes. Before we go to 64-bit, let me show you this treat. Here, this one is open most days on my computer. It's 3,439 pages. It's free. Just download it. Very good stuff in here. It doesn't nearly describe everything the processor does, but it's it's a good start. So I wanted to look at page table. Let's see. There, maybe. Okay. Page directory. This is it. Perfect. Right. So you find a lot of this sort of thing in the developer manual. Generally, the only people that need to read this manual are those that want to write assembly, those that really care about program performance, and those who develop operating systems. Maybe if you do some device drivers, there's some particular things about types of memory and so on. But most of us don't have to worry about it. But anyway, here's what the 32-bit page table looks like. The two pieces we want to worry about right now are this. This is one sort of entry, and then this one here, the page table entry and page directory entry. So the page directory entry is these, right? There's 1,024 of those. Each one says, here. Where is the page table? It's using 24 bits for it, right? These lower 12 bits, you see the annotations maybe a little unfamiliar. So there's 12 bits here at the bottom, and then it goes all the way up to 32. Oh, sorry. Of course, it's 20 bits. What am I saying? 20 bits worth of address. And then there's some ignored bits. This one here is the P bits, the present bit. So the CPU will always check that first before trying to dereference some memory. You'll see, okay, is this actually a valid entry? If so, is it user or supervisor mode access only? If we're in user mode, it needs to be a 1 here. Otherwise, we'll get another one of those page faults. No, you're not allowed to write to this. This belongs to supervisor mode only. There's a couple of other bits that are less important. This one says if this page directory entry has been accessed recently, if anyone's looked at it. This is cache control, cache disable, write through for the cache. Let's ignore those pieces. All right, but what about this here? So the address of the page table, clearly that points at one of these, right? Oops. One of those chunks of 1,024 page table entries. But we only have a 20-bit address. 20 bits, that's only a megabyte. So what's going on there? Why are we okay with just 20 bits worth of address?
Because each one of those page tables refers to a 4K chunk, and 4K times a meg is 4 gig, which would give you your full 32-bit 4 gig address space.
So here we're just looking at one pointer, right? It's a pointer to the page table we want to look at next.
Right.
So I think, you're thinking the right thing. Basically, this is not the address. It's a multiple of 4,096 bytes. So just put all of these to zeros, and you have an address. Right. There's no point in specifying the lower 12 bits of this thing, because it has to be page aligned anyway. It has to start at a boundary of 4,096 bytes. And so we just use the top 20 bits of the address. So the processor will use that to find it's not really the address, it's the number. It's the page number that we're looking for. Okay, so once we have the page number, now we can look up our page table. That's this one. In each page table entry, we have all of this stuff. Same thing, the address of that page frame. Well, it's the number, physical page frame number, right? If you multiply the number by 4096, you get the actual address. Got a beach ball, nice. Okay, so here basically the same deal. The bit has to be present. Oh, it made a copy of my 4,000 page document because I selected something here. Okay, and here if it's 0, well, we don't use it. Okay, there's one more neat little trick, and that's this one here, which maybe well, why not? You can specify that that this page directory entry doesn't actually point at a page table. You say instead it points at a 4 megabyte chunk. So that is the one here, I think. You make this bit a 1, then it'll treat yeah, I don't know what's going on with that one. That is weird. Anyway, so this is called huge pages, if you ever run into it. Huge pages basically just means, oh, we don't do this whole thing. We just make one huge 4 MB huge page. So we can point at one of those two if we want. If you just set the right bit in here. Okay, so that's 32-bit mode. It's pretty much the whole story, except for the little caching business that makes it all go fast. Right? All these extra pointer dereferences would be really slow otherwise. Let's take a quick look at 64-bit as well. I think it was just down here, but let's go like this. So hopefully there's a nice picture. 32. Okay. I suppose that's okay. Yeah. So if you just look at an address, in fact, there ought to be one of those for 32-bit too. Yeah, let's just look from here. If we just look at this part from here, that's 32 bits, from 0 up to, let's pretend it's 32 bits. The first, actually I should draw it instead. Let me do that. So you have this linear address. At the bottom we have 12 bits of offset. That says, so 12 bits. How many, what's the address range of 12 bits? 4 kilobytes, exactly. All right, so we can specify a 4 anywhere within 4 kilobytes with this 12-bit offset. And then we have 10 bits page table entry, right? The next 10 bits up say, which entry in the page table are we talking about here? With 10 bits, we can select 1 out of 1024 entries, matches up perfectly with the size of our page table. And then finally, we have 10 bits of page directory entry. So this one here is a direct index into our page directory, right? Here's another index. Once we know which table to look at, that's the index into our page table. And then finally, the processor will look at the remaining 12 bits to see which byte did we actually want inside of the final page. So this is sort of the annotation we were looking at here as well, right? But it's slightly different in 64-bit. Problem being, our addresses are so big that we now need a lot of page tables. Right? You have, in fact, they go only up to 48 bits. You can only, right now, the Intel processors only support 48-bit addresses. But even that is then, let's see, 32 plus, so, I don't know, countless gigabytes, terabytes, and more. Right? Let's see. So here's a gigabyte, and then there's 18 bits left. That is 256,000 gigabytes. Right? 256 terabytes of RAM is what we can describe with a 48-bit address, and that's probably going to be okay for a while longer. Okay, so in this case, every page is still 4 kilobytes. So that one's the same. And now it gets a little bit different. So a page table actually can only contain 512 page table entries this time. In 64-bit, we can only use 512 page table entries, not 1024, because the number is just larger. Right? Which physical page frame do we want? Well, we need more bits to represent that. We need a 64-bit page table entry. So the page table entry 64-bit, therefore, in 4 kilobytes, we can only fit 512 pointers or entries, and therefore only 9 bits of the address goes into the page table index. Right? It's 512 instead of 1024, so 9 bits. Same thing, we have a directory like before. So this is the index into the directory. And I think they kept a directory name just because that was what they used in 32-bit. And then, okay, what do we call the next one up? Well, we call it the page directory pointer table. Right? So we have pointers to page directories, so naturally that's the page directory pointer table. Okay, so that's another 9 bits that indexes into the page directory pointer table, and then I think they just gave up. So now we have level 4 entry page. I don't know what the M is for. Level 4, so it's the 4th level, right? And that's actually what our CR3 is pointing at now. So we say, here's we still call it a page table. Right? The whole thing is still a page table. All these 4 levels and so on. It's a little confusing that we have a page table here and a page table, the whole thing, but there you go. Okay, so our CR3 is 64-bit, our CR3 points at a PML4. Each one of those entries represents 9992 to the 27. That's lots of megabytes, lots of gigabytes. So we should figure that out. Let's get that right. Programmer's calculator. Oh, there's not a 2 per. Okay. 2 to the power of. Hello. 2 to the power of what? 12 plus 9 plus 9. That's we're at 30, and then there's 38. Right. 39 bits. That's difficult. Let's see. 550. 512 gigabytes. That's probably right. Yeah. Right. Okay. Yeah, that makes sense. 512. That's 9 above. Gigabyte is at 30. So then 9. No. 7 should be. No. 9 is 512. That's right. Good. 512 gigabytes per entry. Right. And then each one in here, then each one in this one points at 4 gigabytes. Is it 1 gigabyte? 1 gigabyte, right? 30 bits. It's 1 gigabyte. So each one of these entries in the page directory pointer table points at a structure for 1 gigabyte, and then this is.
That's 512. That's 9 bits long.
Well, so it's 30 bits total, right? So that'll be an address worth of 1 gigabyte. And we have 512 of those entries. That's how we get to 512 gigabytes total. And here it is then 21 bits long, 12 plus 9, so that's 2 gigabytes per entry in the page directory, right? And then finally 4 kilobytes per entry in the page table. Okay, so again, these don't have to be filled in, right? That's the reason we have this setup. We don't have enough physical RAM for all of this, but virtual address space is also useful sometimes on its own. So it's very nice to be able to represent the entire address space sparsely if we want. Okay, so let's see how xv6 allocates a little bit of memory. So basically, when the process, in our previous example, we had a process just accessing memory willy-nilly. And that's just not supported, we just get a page fault, right? But if we want some more memory, we call malloc. Malloc doesn't have any more heap space. Malloc in turn calls sbreak to increase the size of the heap. So let's start at sys sbreak to see what it looks like. And then next week we'll talk about lazy memory allocation, where you just allocate virtual address space. You say, yeah, you can have more heap space. But we don't actually map anything in. We just leave it alone, and then the page fault comes, and then we say, oh yeah, I was supposed to map that in, and then you find a page that's free, map it in, and return it. That's actually what we're going to be implementing for mmap. All right, so let's take a quick look then at sbreak. Sys sbreak maybe. Oop. Okay, so I'm going to skip the intermediate steps here for a system call. We all know how system calls work now. So basically what sbreak takes is an integer argument saying how many more bytes. You can actually pass it a negative as well, and that means shrink my heap. So here's the normal thing. We find the argument, and then we call growproc to get the to increase the size. So in xv6, processes really are contiguous. In memory, there's at the bottom is the text, and there's a bit of stack, and then there's a heap, and the heap goes straight up, and after that it's empty. At some point we reach the kernel's address space, and we'll look at that memory layout a little bit later. At half the address, half the way up to 2 to the power of 64, there sits the kernel. All right, so or maybe it's 2 to the power of 48. Anyway, let's take a look at growproc. So this is here in proc.c. It's a little hard to tell, but the file name is always down here. I guess if you move forward a few seats, you can probably see it. Okay, so we're only interested in if we want to grow it for now. So that's this alloc UVM. And okay, so we allocate the memory. This actually does all the mapping and things. We'll see it momentarily. And then when we're done, we update the process's size to remember like how big is the heap. And then we do a switch UVM. And this one actually says, okay, now we want to use this new page table because we've updated the page table, and switch UVM will kind of let the CPU know that you can't use your old cache values. So let's dig into alloc UVM. So this was past a pointer. In fact, let me go back. Proc pager, that's the one we talked about from the clicker question. Proc pager, that's a pointer to our current entire page table. Right? It says pager here. Maybe it should say PML4. Right? It's the top level. We're in 64-bit here. Okay, so alloc UVM takes that page table and then the old size and how big we want it to be now. So if we've already hit the ceiling, we give up. Whereas the current base is where the kernel starts, very high up in virtual address space. That's not going to be a problem. Okay. What's going on here is the interesting part. So now we're saying for every page size chunk that we need to allocate, say the new size is 8 kilobytes larger than the old size, probably we need to grow it by 2 pages then. There's some rounding up here. We can only allocate memory. The kernel only allocates memory in page size chunks. Right? So the process is given 1 more page. There is no way to hand out 2 kilobytes to a process. Right? The page table says this page belongs to the process or it does not. So we could tell the process, oh, you can't write behind those beyond the first 2 kilobytes of the page, but the process could still do it. There's just no way to specify the process does not have write access to those 2 kilobytes. It's 4 kilobyte granularity. All right. So we say for each page we need to allocate, first get a page. Okay, so that gets a little bit interesting. Now we get to kalloc. In fact, we should take a brief detour in the other window here to main. At the very beginning here, we say kinit. This is actually the kalloc, a kalloc function. The kalloc is the page allocator. You always get a page back. You get a pointer to a page. Kinit here says all of these pages, this entire memory range is the end of the kernel, like the end of the kernel text or the code, up to 4 megabytes above, or up to just 4 megabytes. So from the end of the kernel to 4 megabytes, those are free pages that we don't need. And so these will be added to a linked list. There's a long linked list full of free pages. So now we know that. Let's take a look at kalloc. And maybe it's not entirely obvious, so let's do the kalloc list here. If we have the time. Yeah, we do. All right, so kalloc looks like this. Okay, we call it struct. We probably have the code there. So I'll just write it like this. We have a free list that points at 1 page. All right, and then from each page, okay, actually let's do it like this instead. That's 4 kilobytes, all right? So we have a long series of those, and in each one of those pages there's a pointer at the top to the next page. That's all it is. So it's a linked list that contains entire pages. Usually a linked list would have this little header, right? It'll just say, okay, here's the next one and here's the value. Here there's no value. We're not interested in values. We don't want a pointer to a page or something. We're interested in the pages themselves. So the free list pointer here points at the first page. Inside of that page is another page, pointer to another page, and so on. So it doesn't use any extra memory, right? There's no, the data structure is present inside of what we're storing here. It's a little subtlety there, but I think it's kind of neat. Okay, so all these 4 kilobyte nodes in our long list, or elements in our long list, are available for allocation. And when you call kalloc, we can ignore this for now. This is just for concurrency. We just find the first entry, right? That's the one we're going to return. We call it a run, but really that's the page pointer. And then we basically take that off the list, right? Point the header to the next on the list. That's it. So it's going to be pretty fast. Allocating a page from the free list is like that. That's nice. Okay, so we got a page. Same thing when you want to free it. right? You free a page, you pass in the pointer to the beginning of the page, you'll just add it to the front of the queue. So it's also very quick to add it, except this thing. Oh, interesting. Looks like it's not full of zeros, it's full of ones. Right? XG6 figured, the designers here figured that it's better to fill it with ones because it's a little more obvious that this is maybe a mistake. Okay, so that's taking a while actually. Does anyone want to take a guess? I kind of like these numbers. How long does it take to fill a page with ones?
In terms of clock cycle?
In terms of seconds or smaller pieces of seconds? Or instructions? Or
50 microseconds.
50 microseconds is our first bid. That means you could do 20,000, 200,000 per second pages. That's not so bad. Any other bids? Half a millisecond. All right, so that's 2,000 per second, right, of page speeds. Actually, it takes about 1 microsecond. There's 4 kilobytes worth. We need to do 512 moves, like 8 bytes at a time. You move a 0 into this and this and this address, right? So in terms of instructions, there's 512 instructions. The only remaining kind of limitation is the bus bandwidth to the memory, and it's incredibly fast. It's something on the order of 20 gigabytes per second. So let's see, 20 gigabytes, that is 5 million pages per second. So that's much less than a microsecond actually, if we want it. But anyway, the instructions are the limitation here, just getting the stores up. Okay, so going back to where we came from, we allocate a page. This is actually pointing at, I need to draw this now, at a mapping. Okay, we need to look at the process address space overall. It looks like this actually. Okay. Oh, it's a little bit ugly. It's okay. All right. So here's a text. All right. Here's our process. Address 0 is down here. We have a text. That's the program code. All right. And then we have, and let's just bake in the global values in the text for now. Then we have the stack. In XG6, the stack is only 4 kilobytes. And we need another piece. Here's our heap. And that one can grow and shrink a little bit. This is empty. Should put a 0 down here. Oh. And then up here, and you'll run into this many times, is kern base. Kern base is FFF8. That is, well, no, it's not FFF8. It's FFF8 and then a whole bunch of zeros. FFF, that's the first 16 bits that aren't allowed in the 64-bit address. You know, the first 16 bits aren't used. That's why that's the 8. It's Fs. And then we have an 8. This is the top bit in the entire remaining 48 bits, and the rest are zeros. So, all right, that should be the full address. Okay, so the kernel starts at half of the address space, right, halfway up. So from there on, we have the kernel's text. Oh. And then we have well, forget the kernel stack. Basically, after that, we have a flat mapping, it's called. Or direct map is better. To our physical memory. Okay, so maybe we have like 512 megs of physical RAM. That's at least the parameters I usually give my simulator. So in here, there's a whole bunch of these pages, right? 512 megabytes worth of pages. They are directly mapped into address space like this. So, in fact, it goes better than that. It's like this. Let's see. Like that. So you'll see this a lot. P to V, V to P, all over the code. The physical addresses are things that we don't ever use. You cannot do a move to a physical address when you're in virtual memory mode. But sometimes we need to know the address still, especially when we want to map something in. In the page table, we're supposed to specify the physical address of the frame, not the virtual address. And so the way it works here is we have a direct mapping. All those 512 megs are sitting straight up here. Every page is mapped in directly right here. And then some of them have another mapping, like there might be a map of one page from here that's sitting in there, right? So now there's a correspondence from an address over here and the correspondence from an address over here to the same place in actual physical RAM. This allows the kernel to directly access every byte in the system without playing with the page table, right? It can figure out, if it can figure out, oh, for this virtual address, you know, what's the physical address, then it just adds kern base to it, and it can then directly address that byte in memory. Okay, so what's happening in kalloc, of course, is we are allocating physical page frames. The list should consist of a bunch of physical page frames, but we can't have pointers to these because we can't address the physical RAM. So instead we have pointers to this mapping up here. So every pointer, we just add kern base to it, and now we have a viable address. So that's what's going on over here. Let's see. Right. So from kalloc, we get an address that points in here to one of these free pages, whatever free pages are in here. All right. We set it to zeros. Aha. So there we set it to zeros again. So it's 1 from k-free. Oh, interesting. Okay. When you free it, you set it to zeros, and then when we provide it to the user space, we set it to ones. So in case we kind of lose one somewhere, we can see the difference. Okay. So and finally, we call map pages, which says, okay, and it's pages, but it's really just the one page. In this case, we say, oh, here's the address, right? And it's 4 kilobytes. We want to map this one in. Sorry, at this address is where we want to put it. We're going to add a new page at this address. Here's the physical page frame that we want to map in. So that's the mem that we just got out of kalloc, a free page. And we say v to p, that actually subtracts kern base from the address. That's all it does. It's kern base minus, address minus kern base. Okay, so let's take a quick look at map pages to see what that one does too. I think we're going to have to skip one step. Yeah. So here, we'll return to this later. We find the page table entry. So this one is multiple steps to it. We're going through this whole thing. This whole 4-level, actually I don't even have it here, but we're going through the 4 levels of the page table to find the entry at the bottom right here. Now we're going to write to this entry. Let's see what that looks like finally. Oh. So actually putting something in the page table is just this assignment. There's nothing more to it. Right? Page table entry is an address, physical address, and then some permission bits, and finally this present bit. You make that assignment, and now suddenly another page appears in memory. So we're out of time. But next time we'll also look through this walk page here just for completeness. Okay, have a good weekend and good luck with the homework. I'll see you on Tuesday.